All right, so here's a quick overview of what we'll cover today. We'll start by giving a project overview and some important background information, and then we'll dive into some of the key findings from our foundational research. After that, we'll walk through some of the infrastructure recommendations that we've developed based on that foundational research. And then the University of Cincinnati will walk us through the case studies that they've been conducting in the field and with their driving simulator. And then finally, we'll give you a preview of the web-based resource that we're building to help support the implementation of our guidebook. All right, so starting with a project overview. So this project really started with one central question. How does the physical infrastructure influence the operational design domain of driving automation systems? So our objective throughout this project was to develop recommendations for infrastructure maintenance and design that could help infrastructure owner-operators or IOOs that were seeking to prepare and support AV deployments. So our recommendations primarily focus on the physical infrastructure elements, but we also touch a bit on digital infrastructure where we find it relevant. So this is a 3-year research initiative, and it's scheduled to conclude in November of 2026. So with that being said, we're a little bit more than halfway done with the project. So we've completed phase 1 and are currently in phase 2. So as a part of this phase, we're collaborating with Dr. Ahmed and Dr. Nazal, who are conducting both the field testing and driving simulator case studies. And then we've also been actively sharing our research at conferences and webinars like we're doing today to help circulate awareness of this resource that we're developing. So the purpose of our work in phase 2 is to gain some valuable insights so we can refine and validate our infrastructure recommendations, which will ultimately feed into our revised AV infrastructure guide. All right, and now I'll pass it off to Katie to dig into some important background information.
All right, so first we want to set the stage with some background on how automated driving systems work and how infrastructure plays a role. So the dynamic driving task, or DDT, refers to real-time operational and tactical functions involved in vehicle control. And here we can see some examples of operational functions and tactical functions. Automation of parts of the DDT is what enables automation systems. Driving automation systems are classified into levels of driving automation, which many are probably familiar with. These define the division of responsibility between the automated system and the human driver. The levels range from level 0, where the human is fully in control, to level 5, where the vehicle handles all driving tasks under all conditions. And we can categorize these levels into 2 main groups. We have advanced driver assistance systems, or ADAS, for the lower levels of automation, and automated driving systems, or ADS, for the higher levels of automation. And every driving automation system, whether it's ADAS or ADS, has an operational design domain, or ODD. The ODD defines the specific conditions under which a given driving automation system is designed to operate safely. ODD requirements may include factors such as road type, surface conditions, speed, lighting conditions, and weather. It's important to note that the ODD is defined by the vehicle manufacturer or technology provider. So the exact ODD of, for example, a lane keep assist may differ slightly between manufacturers, but there are going to be many consistencies between similar applications. So for something like a lane keep assist, most ODDs would include clearly visible lane markings, and the visibility of the lane markings could be influenced by several factors, such as the lane markings themselves, road surface quality, lighting conditions, etc. And last slide in the background, beyond automation, connectivity plays a really important role in AV readiness planning. So connected vehicle, or CV technology, allows vehicles, bicyclists, pedestrians, and infrastructure to communicate in real time. So for example, digital infrastructure such as a roadside unit or RSU in a work zone might broadcast a lane closure alert. And this alert could be received by a human driver who would adjust their behavior, or by the driving automation system, which would incorporate that information into its decision making. So connectivity adds this extra layer of intelligence to the driving task by providing contextual awareness that the sensor would not otherwise have. Okay, so moving into the project itself, to build a strong foundation for our recommendations. The project began with an extensive literature review. So this covered academic research, federal studies, and regulatory guidance. And this literature review revealed 6 core categories of physical infrastructure that have a direct influence on the ODD of AV systems. And you can see these on the right side. These are pavement markings, roadway surface, traffic signs, traffic signals, temporary traffic control or work zones, and geometric design. And so what we found in the literature was that inconsistencies in the design, placement, or maintenance of these elements can significantly limit the vehicle's ODD. And then when these inconsistencies exist in unpredictable conditions like a work zone or a school zone, it presents an added layer of challenges for the AVs. And then next, shifting into digital infrastructure. Digital infrastructure is considered an enabling technology, and it can help AVs overcome challenges tied to physical infrastructure and operate in more complex driving conditions. So it provides that critical context beyond what the onboard sensors can detect. And we looked at several aspects of digital infrastructure, and those are shown on the right side of the screen. Something that stood out is that ITS deployments are increasingly used as a readiness metric when evaluating how prepared an area is to support CV-enabled infrastructure. And then finally, while the literature was a really important starting point, it came with some clear limitations. First, because much of the AV industry is for profit, there's a disincentive to publish deficiencies with AV technology. And as a result, there were limited reports on disengagements and control algorithm errors, especially in complex environments. And finally, most of the published studies that were available were conducted in academic settings. And these often will use non-production grade AV systems and tools, and they may not fully reflect what is happening in the real world deployments. And now I'm going to hand it back to Samantha to talk about some AV industry feedback.
All right, thanks, Katie. So we've covered what literature tells us, but as Katie discussed, there are still gaps in the literature, especially when it comes to those real world deployments. So to help fill those gaps, we engaged directly with the AV industry stakeholders. So that included developers, manufacturers, and testbed operators. So this next section summarizes the key themes and concerns that we heard from those conversations, and then how that feedback helped shape our recommendations moving forward. So some common themes that we heard included the need for uniform infrastructure across markings, signs, and signals. And when consistent and uniform infrastructure is lacking, HD maps are a critical tool that can help the AVs overcome some of these infrastructure gaps. We also heard that AVs struggle most with unpredictable road users, especially in ambiguous situations that can be caused by degraded infrastructure. You could go to the next point, and the next one. They also talked a lot about the shared benefits, so the infrastructure improvements that support AVs also enhance the safety and the clarity for the human drivers. And then finally, to spur the safe adoption of AVs, it's essential to educate both the public on these systems' capabilities as well as their limitations. All right, so moving on to some common key infrastructure investments that we heard from these conversations. So within the realm of physical infrastructure, we heard that pavement markings should be highly visible and applied consistently across jurisdictions. So that includes ensuring a proper contrast, color, pattern, and design. We also heard that there's a need for better separation and channelization of the non-motorized road users, especially in urban areas. And improved sight distance is especially critical at permissive and complex intersections where AVs may need to rely on more visual input in order to make decisions. And safe harbor locations, also known as shouldering areas on highways, provide critical fallback zones for AVs when these disengagements occur. Now, looking to the digital side, the industry is looking for real-time information about work zones, crashes, and special events, all centralized through an API like the Work Zone Data Exchange or Cellular Vehicle to Everything. They also emphasize the need for emergency vehicle data, as the presence and routing information can help AVs respond appropriately in these scenarios. And then finally, AVs benefit from access to real-time signal phase and timing information to help improve their navigation and reduce risks at intersections. So now that we've explored the challenges and insights from both research and the AV industry, we can shift into the core of our project, which is really our infrastructure recommendations guidebook. So these recommendations are organized by infrastructure category based on what we found to have the biggest influence on AV's ODD. So these recommendations are split into 8 different categories that are shown on the screen. So it includes various elements of the physical infrastructure, as well as digital infrastructure, and then different policies and procedures that are important to consider. So today we'll mainly focus on the physical infrastructure recommendations, since these will feed directly into the case studies that Dr. Ahmed and Dr. Nizal will be presenting on later. So starting with recommendations for pavement markings. FHWA identified these as the top IOO investment to help broaden AV's operational design domain, or their ODD. So well-maintained pavement markings support both level 1 and level 2 ADAS that heavily rely on their camera perception algorithms, but they also help support the level 4 fleets, which are mainly using their HD maps, but still relying on markings to help with the real-time lane validation. So given their importance, it's not just about having the pavement markings in place, it's also about maintaining their quality and their consistency over time. And while standards for implementing these markings are established in the NUTCD, there's still a growing need for stronger asset management practices to help ensure that these markings are remaining uniform and high performing across the network. So from an AV's perspective, research points to 2 primary factors that are influencing how well these markings are detected. So that includes contrast and retroreflectivity. Contrast appears to be one of the most important measures for machine vision detection, with studies suggesting a minimum contrast ratio of 3:1 for reliable lane recognition. Retroreflectivity also plays a major role, especially in the low light and wet conditions. Literature indicates that a minimum value of 150 millicandelas per square meter per lux is needed for this consistent detection. Now, pavement marking design can also help AV systems better detect the lane markings. So wider 6-inch longitudinal markings give AV cameras a larger and higher contrast target, essentially providing more pixels for their detection. The National Committee on Uniform Traffic Control Devices recommended updates to the MUTCD based on their research on incorporating ADS systems into highways. So they recommended the use of 6-inch markings on all freeways, expressways, and ramps, as well as on all of their roadways with speed limits greater than 40 miles per hour. And they also recommended the use of 6-inch edge lines for all 2-lane roadways. When raised pavement markings or RPMs are used alone, or if they aren't maintained, they can actually hinder machine vision from reliably detecting the lane markings. So it's recommended here that RPMs are only used as a supplement to the painted markings, and they shouldn't actually replace them. So that means that non-reflective RPMs, sometimes referred to as box dots, also shouldn't be used as a standalone lane delineation method. Level 1 and Level 2 ADAS systems like Lane Keep Assist rely heavily on their vision-based perception algorithms to help identify lane boundaries and maintain lane positioning. So when pavement markings are missing for more than a few seconds at normal driving speeds, the vision-based system may be forced to disengage. So sometimes access-controlled facilities, which are the most common operating environments for the Level 1 and Level 2 ADAS systems, will sometimes lack these lane-specific markings, especially at ramps, diverge points, and in merge areas. So to improve reliability in these locations, it's important to include dotted line extensions along all entrance and exit ramps, as well as on aux lanes. And chevron markings within gore areas are important to clearly help distinguish the exit lane from the travel lane. Now, similar to access control facilities, missing pavement markings in complex driving environments like intersections can significantly limit the effectiveness of AV technology. Most Level 1 and Level 2 ADAS systems aren't designed to operate in these environments, so this recommendation is really impacting the Level 3 and Level 4 ADS deployments. So when navigating an intersection, dotted edge line extensions provide crucial wayfinding points for these vehicles. And this is especially beneficial for intersections with more than one turning lane, those with unique geometry, or sharp turning radius. Now, representatives from the AV industry also recommended that pedestrian crosswalks, bike lanes, and bus lanes be distinctly marked to enhance their visibility. So by using colored pavement markings, this can help distinguish these areas from the regular traffic lanes. All right, so moving on, there are various roadway surface characteristics that can influence the performance of machine vision algorithms. So this includes the use of, next slide, pavement crack sealers, which can appear similar to the lane lines, especially to ADAS technologies like lane keep assist. So the best practice here is to select crack sealing materials that blend in with the pavement and are easily distinguishable from the lane markings. With regards to potholes, we noticed that in our field testing, level 3 Teslas didn't consistently slow down when they encountered a pothole. So in some cases, that can lead to steering issues, especially on some high-speed corridors. The best practice here is to implement a proactive pothole management program that includes regular monitoring and prompt repairs, especially on these high-speed corridors. Moving on to traffic signs. AVs rely on 2 layers of machine vision algorithms to really interpret traffic signs in real time. So this first layer is a detection algorithm. It will scan the roadway and then flag any object that looks like a sign. And then once that happens, a second layer, which is the classification algorithm, will then review the detected image and determine what type of sign it is. So this 2-step process will allow for AVs to quickly react to signage, but it also means accuracy depends heavily on the consistency of what the system is seeing in the environment. So machine vision systems rely on this template matching to compare features of a detected object to a database of known sign templates. So when sign colors, sizes, shapes, or symbols vary, or when non-standard or unique signs are used, the system may misclassify the signage. Sign visibility is also impacted by overcrowding or occlusion, which is typically more common in the dense urban environments, where sign visibility is more likely to be reduced. Now, proper sign placement is also important. So factors like height, lateral offset, and angle determine whether the system perceives the sign as applying to its current lane. So in the top left photo, for example, we see the AV misinterpret signage from a nearby frontage road as being an applicable road rule for the freeway. And when it comes to electronic and dynamic message signs, AV developers share that these present a unique set of challenges for the perception systems. So the biggest technical challenge is related to the sign's brightness and their refresh rates. So if a sign's refresh rate happens to synchronize with the vehicle camera shutter, the sign may appear blank or just unreadable to the system. Now, variable speed limit signs were also mentioned as a specific pain point, with difficulties distinguishing these signs as regulatory. And just like with standard signage, consistency in color, shape, size, and mounting position support better detection. Also, maintaining flicker rates greater than 200 Hertz can really help ensure that the AV cameras are reliably capturing and interpreting the displayed message. Now, crosswalk signage, like in pedestrian signs typically used in school zones, present some other unique detection challenges. So these signs are typically smaller, mounted lower to the ground, and often use smaller text and symbols. So that reduced size and height can make them less visible to AV perception systems. And then they're also more susceptible to occlusion. So being blocked by a vehicle up ahead can cause that occlusion, which makes it harder for the detection systems to consistently identify them. So the best practice here is to install crosswalk signage at standardized heights and in locations that really maximize their visibility to reduce that risk of occlusion. Now, as AVs become more common, dedicated infrastructure and signage for bicyclists will play an increasingly important role in ensuring safe interactions between all of the road users. And because bicyclist movements can be unpredictable, AVs rely on clear pavement markings and consistent signage to help their perception systems anticipate the merging, crossing, and yielding behaviors. To enhance safety, bike lane signage should be installed where a lane ends and merges with the general traffic, and advanced warning signs should be placed before that transition zone. And when we think about future methods for AVs to read roadway information, one concept that's been explored is the use of QR codes that could be detected exclusively by the machine vision systems. So AV industry representatives have expressed this interest, but have also emphasized that in order for these technologies to be effective, they really need to be deployed consistently and at a scale nationwide before the integration into their systems would be worthwhile for them. Now, similar to signage, AVs rely on two machine vision algorithms to detect and then classify the state of traffic signals for a specific lane. And the challenges and risks associated with an AV navigating an intersection is really dependent on the vehicle's trajectory, the infrastructure elements denoting the intersection, and the behavior of the other road users within or neighboring the intersection. So the ability of an AV to detect a traffic signal state is heavily influenced by their size and brightness of the signal head. Research and feedback from the industry suggests that 12-inch signal lenses are preferred over 8-inch ones because the larger diameter provides a more distinct and easily detectable light source for the onboard cameras. One AV industry representative also noted that LED signal heads are significantly easier for the perception systems to detect compared to older incandescent bulbs just because of their sharper light contrast. And signal head visibility can also be improved by using black or yellow backplates, especially in areas where overcrowding of other signals and signs may be an issue. And anything that reduces the visibility of a traffic signal increases the chance that an AV could misclassify its state. So traditionally, optical programming and mechanical louvers are used to control the viewing angles and reduce glare for human drivers. But for AVs, these same mechanisms can actually limit the field of view for the onboard cameras, making it harder for them to detect and correctly interpret signal indications. And because of that, the recommendation is to minimize the use of optical programming and louvers wherever it's possible. But if they're necessary, mechanical louvers are preferred since they typically allow for better signal visibility within a controlled angle. Flashing indications and beacons present interpretation challenges for AVs similar to the issues encountered with refresh rates of electronic signage. So for instance, RRFPs can be difficult for AVs to detect reliably because of their rapid flashing patterns and their inconsistent refresh rates. And in these scenarios, AVs must depend more heavily on their pedestrian detection systems and predictive algorithms to determine when to yield for pedestrians. So the best practice here is to use solid signal indications using standard colors like green, yellow, and red over flashing beacons wherever it's possible. Now, work zones present some of the most complex challenges for AVs because of their dynamic nature. Industry representatives have noted challenges in work zones extend across nearly every type of physical infrastructure, from pavement markings and traffic control devices to signage and barriers, all of which can sometimes differ from permanent roadway standards. So one of the most persistent challenges for AVs in work zones is their ghost markings. So to address this issue, several DOTs, including Kentucky, Wisconsin, California, Indiana, and Texas, have been piloting the use of orange pavement markings to help clearly distinguish temporary lanes in work zones. So a joint study conducted by Indiana and Purdue found that AV systems detected orange markings with 100% accuracy, which was comparable to standard white and yellow markings. The AV industry representatives have also expressed strong support for the strategy, noting that a contrasting color like orange can significantly improve lane detection, especially for long-term work zones. Kentucky's testing also showed that retroreflectivity standards for orange markings can be met when high-quality bead packages are used, making this both a practical and effective solution. Now, the presence of roadside workers presents a unique set of challenges for AVs in the work zones, especially when there's no physical protection like a concrete barrier separating them from the active travel lane. And because pedestrian intent can be hard to predict, workers moving near open lanes or between cones can cause a level 4 ADS system to slow down or even stop completely as a safety precaution. So wherever possible, workers should be physically separated from the roadway using barriers to help minimize these interactions. Also, V2X communication technologies can enhance safety by allowing AVs to detect and respond to workers more effectively. Some emerging tools use connected devices mounted on phones, light fixtures, and even workers' vests to transmit position data, helping to alert the AVs of nearby human activity and helping to prevent potential conflicts.